Good morning everyone, I'm your presenter Jae-sung Choi. Let me start my presentation about stereo object matching network. The paper ID is 3544. First of all, what is stereo matching? Given left and right images, the purpose of this task is to find pixel-wise correspondence between two images, which is called disparity. While recent deep learning-based methods largely improves quality of disparity, the disparity uncertainty nearby object's boundary still remains problem. To overcome this issue, we propose stereo object matching network that combines stereo matching and 3D object detection for instance level stereo matching. Given stereo images, we first extract the shared coarse volume that is used for stereo matching as well as 3D object detection. The key idea of our method lies on how to use the shared coarse volume. Let us shortly revisit the concept of differentiable coarse volume. The coarse volume is the volumetric representation of camera rays to encapsulate the 3D world in a view of referential camera. Our idea starts from its definition, and we extend the usage of coarse volume for 3D object detection as well. It can be thought of the part of the coarse volume becomes instance level volume that can describe headings or positions of each vehicle. However, as I visualize in the left figure, the 3D attention within the coarse volume is only valid for the surface of vehicle, not visible voxels, for instance, inside of vehicles. Accordingly, it is required us to process the additional steps to properly link coarse volume to detection branch. Before we concretely describe our contribution, we firstly explain the overall architecture of our method. First stage is coarse volume prediction, which estimate image feature maps as well as the initial coarse volume from the given stereo images. Second, 3D object detection branch, which performs 3D vehicle detection with the help of 3D region proposer network and header network. Lastly, disparity regression branch, which finally regresses disparity map from the initial coarse volume. Finally, our network is designed to estimate disparity map as well as 3D vehicle detection. Then let us describe the details of our detection branch, including the bridges that smoothly link between coarse volume and detection branch. This is a brief sketch inside of detection branch that consists of ROI select, fusion by occupancy modules, and header network. Simply, given shared coarse volume and estimated disparity map from regression branch, detection branch infers 3D vehicles information such as vehicle's position and heading information. The first module, ROI Select, is trained to extract object level volumes from the shared coarse volume. The first module, ROI Select, is trained to extract object level volumes from the shared coarse volume. In the figure above, 3D ROIs represent the cropped volume that may describe the information about 3D vehicle in camera viewpoint. Along with the 3D ROIs, we also extract 2D patches from disparity map, which is called 2D ROIs in the figure above. Based on the extracted 2D ROIs and 3D ROIs, the purpose of the next module, Fusion by Occupancy, is to blend these 2D 3D ROIs in a 3D structured manner. In details, we design 3D occupancy ROI that is back-projected result of disparity patches in 2D ROIs. The purpose of 3D occupancy ROI is to mask voxels inside of vehicles. Thus, detection branch only affects surface of vehicles and refines 3D surface attention within the cost volume during training session. Finally, Fusion by Occupancy estimates the fused 3D ROI, which is the input of the header network for the estimation of heading and locations of 3D vehicles. In summary, the two novel bridges modules, ROI Select and Fusion by Occupancy, is designed to extract surface attention nearby vehicles for refinement of the cost volume during the training session. Based on our architecture design, we train our stereo object matching network in an end-to-end manner while applying multitask losses such as disparity loss, region proposal loss, and header loss. We measure the quality of estimated depth from hours and related works that also conduct stereo matching and 3D object detection. We obtain higher accuracy in depth performance in Kitty eigensplit benchmark and virtual Kitty benchmark. Moreover, as you can see in the red rectangles at the right figures, our method correctly reshaped the roof of the vehicles while previous works failed to capture the depth values at the boundary of the vehicles. Such results support the necessity of our bridge modules, ROI Select and Fusion by Occupancy, that are trained to refine the 3D surface attention of the cost volume for better estimation of disparity map. We also present the qualitative result of our detection result. As you can see in the table above, unfortunately, we did not fully achieve the highest accuracy compared to the other methods. We guess this reason for direct usage of the cost volume. Recent methods focus more on the detection task, so they utilize metric unit representation such as point clouds or geometric volume. This fundamental difference leads to the performance gap of detection as well as stereo matching. Conclusion. We propose stereo object matching network that utilize 2D pixel information as well as 3D object information for accurate disparity estimation. We focus on bridge modules, ROI Select, and Fusion by Occupancy that are designed to refine 3D surface attention at shared 3D feature volume. Thanks to detection guidance, our network obtains state-of-the-art performance in depth estimation compared to previous methods. Thank you for your listening.